dynamics or brain dynamics and other kind of things interesting. Basically, what we have when we measure some physics or some experiment is what we can do. We try to infer from this set of measure, try to infer which is the kind of dynamics that we want to study. In this relation, basically, I don't need to explain that we have a set of equations, a set of couple equation, and we can try to do is identify the interaction, but an important thing, I think, especially when we try to identify the dynamics, is this dynamics is provided by an stochastic dynamics or the dynamic nonlinear dynamics or something that is not stochastic. Why? Because that we want to define is we say, okay, we have my set of measures, and these measures are provided by stochastic dynamics or some nonlinear dynamics, something that is another kind. Because this is the approach that we want to describe this set of equations, or this set of measures. If the system is able, if we are able to show that we're seeing something that is nonlinear, we can deterministic in some way, we can say, okay, we can dominate it by description of this set of measures, like set of some modes, collective mode. But if not, we need to describe with a statistical description. Yeah, this is the difference. Okay, that this is, I think, is everybody knows this kind of thing. Okay, we can continue. But why we need to differentiate in some way stochastic from chaotic dynamics? That is different properties. Normally, what we have the difference is subtle because we know, if we know the equation, we can immediately know that we are simple equation or whatever we have. But chaotic and stochastic dynamics have the same or share some characteristics, like a wide band. We can make it a Fourier spectrum. It's characterized by a wide band power spectrum. The power spectrum usually have with the frequency have the relation f to the minus k, with k greater than equal to 0. This is I call a K noise. That's this characteristic. The autocorrelation function is kind of delta. This is very sharp and decrease. And of course, the behavior, I mean, if we graphic the behavior of the signal, of the data, is very irregular. Okay. Okay. ¿Qué pasó? Okay. The- entonces, okay. What is the principal characteristic that we have in the case of chaotic dynamics? Mm. Everybody knows that the chaotic dynamics have sensitivity to initial conditions. Yeah, this is the principal property, or property or whatever. We want to justify the use of information theory just by this reason. But I want to explain better. Suppose that you have two initial conditions. As here we have two, but this initial condition that we represent by X1 and X2 that of time is, but these are very close in the phase space. Yeah. They are very close, and they are in a ball of radius r, but we are not distinguished between these two initial conditions because this is a problem of the precision that we are making the measures or something. And then basically, something, but and then we observe what happened after some period or some time, posterior time that we measure. I want to see. Oh, understand? Okay. Basically, this is what I say. Okay. We have these two initial conditions in a ball of some in the phase space. These are indistinguishable at this due to the experimental conditions, error that we are measured, and now they are evolved in time, and we observe that after some time, I call this time T star, the two, due to experiment, due to chaotic dynamics, they expand, and now the difference or the distance between the two conditions are differentiated. This how we can now this posterior time we can differentiate it, and these are because the difference at this time T star is expanded with the in the exponential of the Lyapunov, the biggest Lyapunov exponent by the difference of time. And how we can understand this condition? This means no, okay. This is basically what we have. This implies that the instability is some kind of instability reveals some information about the phase space population that we have we don't have at early time. This is why this is the interpretation how we started with the two initial conditions. Initial that was in principle indistinguishable, and now after some evolve in time, they are distinguishable because this kind of thing, and this give me a link. We can think of the chaos or the chaotic dynamics as information source. It's easy, and this is the justification why we can use quantifiers defined in information theory to describe or differentiate between chaotic dynamics and stochastic dynamics. Yeah. Of course, but basically the quantifier that I like to define or define as an application are basic entropic measures. This is the most traditional. That means the Shannon entropy, Salus entropies, Range entropies. Also, we can use the Fisher information measure, and finally, the generalizes statistical complexity and some applications. Well, in the case of the Shannon entropy, this is a global entropy. Is defined usually f logarithm f, it is the logarithmic entropies. It's important to remark that this is the global character. It is not so sensitive to a small change in the probability distribution that is in function of the f, or probability distribution. The Fisher information is defined like the information of the gradient information. It's defined in this way. This is local information because it's more dependent of the probability distribution, small change, and this is important. By this reason, you will see why it's interesting to calculate also the Fisher. Of course, now, I say, we are measures. Then we need the corresponding discrete version of the entropies, the Fisher, and so on. Usually, the Fisher information we can write using. I can write in terms of the amplitude probabilistic. In this case, we don't have a problem with the division of where the probability will be 0. By this reason, we can define the Fisher in this way, representing the probability distribution like this difference, like a distance, a kind of distance in between the probabilities. And this is also important, give me the particular behavior of the Fisher information. But what happened with complexity? When I say, well, what means by complexity? In the morning, somebody said me, what you mean with complexity? I said, oh, okay. Complexity is something difficult or quite general for defining. But I remember when I started to work in this kind of things, almost some time ago, I looked in the dictionary what means complexity, and the definition that the dictionary was complex is something that is not simple. Oh, good. There's the definition for the opposite, but I say, how can I do it? How can we can define? How can I evaluate the complexity in order to have a more precise evaluation. Well, there are in the last years different approach or different definition about how we can define the complexity or statistical complexity, because we are working with the information theory. The first one is definition given by Schinner, Davison, and Landsberg. They say, okay, it's a function of the order or the disorder, and multiply, this is the behavior. They say is the entropy or the degree of or some measure of the order by multiplied by the disorder, but the disorder in this case is 1 minus h. But this is something that is quite similar. Don't give me new function that we want to say, okay, complexity, of course, will be related with the degree of order or some entropy value, but it's not in so simple way. The second is a proposal by Lopez-Ruiz, Mancini, and Calvet. They say, no, we define the statistical complexity like a product between the degree of order, as some entropy measure, times the disorder, something related with the disorder, that in this case is the disequilibrium, because we assume that in the equilibrium state, the uniform or the equilibrium state is described by uniform probability distribution, but have some problems because they take this disequilibrium or this difference of the probability between the system, your system that you are studying, and the probability of the equilibrium, the uniform equilibrium, have some problem because they use the Euclidean distance or the Euclidean form from the distance. This is that we change. And finally, we change is our definition of statistical complexity. That is, we propose with a modification of the Lopez-Ruiz-Mancini equation for the statistical complexity. Okay, we can call the Martin, Plastino, and Rosso, of course. And we replace the term of the disequilibrium in terms of the Jensen-Shannon, or the Jensen, and the divergence of Jensen. Why? Because in this case, the Jensen divergence we can write in terms of the entropy, and in this way, you have a statistical complexity all in terms of the entropies. We can see then the corresponding expression, or whatever other entropies formulation that you use for define, I mean, in terms of Salis or in terms of ranging. Okay, but this is why the complexity, and the idea is how we can define, or how we can define the situation. As I say, or inspired in the dictionary, that they say something complex is something that is not simple. We can say, okay, we can say in terms of patterns, or in terms of the complexity, I say, Okay, a regular pattern, like this. We can say H, we can say is something ordered, something completely irregular. We can associate like disorder, completely disordered, and we say, okay, this have a H equal 1, and something like in this picture, we say, well, it's something that is between both cases. I see some kind of pattern, and also the most important is we can see inside the figure, we can see, discover new patterns and new patterns, new details. The idea is that something like in the extreme case, that means H equal something completely ordered, this is nothing, is not a complex system or complex describer, and also H equal 1, something that is in the case of totally disordered or in the equilibrium, also will be complexity equals 0. The idea is that in between the both, we can have something H different to 0 and anti-H and complexity equals 0. Different to 0, that this is the chaotic regime. The idea is, what I say here, is we can think as a system due to the huge dynamic, produce some kind of dynamics that is much complicated, more irregular in some cases, but than the simple equation that they generated this system. Of course, when we say periodic motion, is nothing complex because we can immediately associate it with something regular. And white noise, of course, is not complex. This will be the extreme case. This is what I say. This is the idea. Something in between. We can see what happened in the term of two physical systems. We can compare a crystal. A crystal is defined in a specific in the red and in the network by minimal information. As we can measure in terms of information, how much information we have in the case of crystal. We can have associated this with the probability distribution of the network, and we have the maximum, the difference between our probability distribution and the equilibrium is given by the maximum distance. It's completely different. In the case of ideal gas, is a completely disordered system. The maximal information is stored in the system. The probability distribution in this case is the equilibrium. And we have the minimum disequilibrium in terms of the probability distribution of the system that we are trying to analyze the other. This is the expression, or the general expression that we say in the case of the complexity is the product between the normalized entropy of normalized and the disequilibrium. Yeah? And we can see this, the case of the crystal, this one extreme, very ordered system, a very disordered system, we also the complexity goes to 0, and we have something in between. And the maximum, or something, where I have the maximum, we have the maximum complexity. Possibly, this we can identify with a chaotic system. Okay. But now it's time to define in more precise way what we can define the entropic function of the degree of disorder. We can define, okay, we suppose that our probability distribution associated with the system that we want to describe is given in this term of general. We define normalized entropy. The normalized is convenient because it has defined this the information that contained in my probability distribution divided by the maximum value. For the disequilibrium, we remember also a definition, proportional or definition, normalization constant. By the distance, we say the idea is use some distance between the probability distribution and the equilibrium distribution, or the normalized equilibrium distribution. And this, if it will be different to 0, you have some information about some privileged state. That is, and this is something that will be very important for the description of in terms of the probability distribution. For the measure information, we can use the Shannon entropy, the usual logarithm P minus P suma sobre P logaritmo de P. We can use Salis entropy. We can, or score Salis, this is a definition. We can also use Range entropy. These three are dependent of some external parameters. In the case with Q equal 1, we have immediately returned to the Shannon entropy. For the case of the disequilibrium, we can adopt different expression. The usual, or the use that proposes by Lopez-Ruiz, Mancini, and Calvet, they propose to use the Euclidean distance between the component, the probability distribution. But the problem is the Euclidean distance is not a good distance in the probability space, something different. The idea is we can use the Guterres distance. The Guterres distance is a distance that is provided by the quantum dynamics, and is basically defined in terms of how the two vectors and the angle. We can do this, or we can define the disequilibrium in terms of a statistical probability distribution. In terms of probability distribution, we want to compare the probability distribution of my system with the probability distribution of the equilibrium. Okay, we can do it with relative pullback entropy. But the problem is that in the case of the pullback entropy, we can have some problem with when when P does, or component of the the component that we divide the probability distribution will be 0, and then again is indefinite. But we can use the Jensen divergence. The Jensen divergence is a symmetric value of the curvac. That is much better. We have, in this case, we don't have a problem with indefinition with something that probability will be 0, in particular, but it will be 0. And of course, we must do, if we use Shannon for the entropy measure, we can use Shannon again in the disequilibrium, or we can use the corresponding version of the Jensen divergence in the case of Salis, or in the case of Renji, or whatever. Yeah? We must be something coherent. Or you can make some definition with a mixture between different measure or functional form for the disequilibrium and the entropy. No problem. The problem is what is better for your study. Okay, then we define the generalized complexity, the difference product between the measure of normalized entropy measure times the disequilibrium between the two probability distribution, the probability distribution for our system that we are trying to analyze, and the distance to the uniform probability distribution. ¿Qué pasó? Okay, this is a little bit more definitions of visualization of the disequilibrium. In terms of the Euclidean distance, of course, you have two probability distributions. We began thinking like two vectors or 2 points in the phase space. With the Gutter is a measure in reality of measure of the angle between these two. And the case of relative probability distribution is again here. The problem with this probability could be 0, and this will make it indefinite. But okay, no problem. We can use the symmetric. The interesting thing with this measure of statistical complexity measure is that if we analyze what happened with the probability space, we remember that the probability space must be something like this. Okay, this is when I consider only or between like the sum. Well, here we have say, okay, we have n, yep. We have, but we can represent it in three. We can take a representation in 3 dimensions. This is the 1, 2, 3. This is what represent our probability space, and this will be interesting to see what happened with this probability space that we want to define how we can evaluate it. We can. Interesting is here is the barycentrum. The barycentrum in this case is just the probability distribution, is all the equal 1 over n. And we can see what happened with the expression for this in terms of the general expression, and we find that for determining for each value of the entropy, of the normalized entropy, we have a range of complexity values. This means that this complexity, or statistical complexity, can give me a new information that is not included in the probability in the Shannon or the information, the Shannon entropy, or Sally's or the others. It's dependent on this. In the I have okay, it's interesting for the practice. You can calculate the statistical complexity, by example, for the case of logistic map as a function of the logistic parameter. And you can see the maximum depend, the curve of maximum and minimum complexity depend only of the dimension of the probability space that you are working. This means if you have a probability, the dimension of 3, I have two curves, but it depends only on the probability, the dimension of the probability distribution that you are using for describe your system. This means the complexity curve or maximum is depend only, well, dependent of some value. I can give you the value. It's not necessary to study the paper, the corresponding paper, because it's a little complicated. Doesn't what to do except count, some algebraic count of organized. And this is they have the only difference in the case of Euclidean, have the maximum complexity curve, but we go por encima, and this is the maximum complexity, the minimum complexity curve, and this is the opposite in the case of the Wouters and also for Jensen-Shannon. That is usual to see. Okay, this is interesting. That is great application. We can check that here. That is the curve. We can generate it at all the real value for the characterization. This gives me the we can define normalized entropy and the complexity. This is we call normally the plane entropy complexity plane. And this is something to show that effectively we are not invented. This is the case of Sally's entropy and Renyi, and also in the case of Sally's and Renyi, we have an additional parameter that is a Q. We can see in the case of Sally's is like all the different curve goes to form some kind of jaw, triangular jaw. In the case of the Renyi, is started to expand. Okay. This is something, again, how you see in the case of normalized entropy and the case of different, for the case of Jensen-Shannon divergence for the disequilibrium. And we can see here the different areas, and we are increasing the number of the dimension of the probability distribution that we are using to describe this. The area starts to expand. The idea is, if we can understand a little, we can see, in reality, the maximum the curve of the continuous minimum of curve, we have one. This is the minimum here. The minimum curve is given by the diagonal, the maximum, the pyramid, and the rest, this is a segmented curve is probably is given by the non-consecutive sides of this pyramid. Yeah? But anyway, you can look at how is the dimension, and you can graphics with enough definition, we can see. Okay. And then, summary. In summary, what this we can say that this statistical complexity measure is able to, we will see that is able to detect dynamical process, and then in the data set. It depends on two different probability distribution. One is associated with the system under analysis, that we call this probability P, and the other is the uniform distribution, P. The further, we know, we can show that the given value of the entropy, or the normalized entropy, is a range of possible value for in between a minimum and a maximum value. That give me the statistical complexity. Yeah. And this is the conclusion, well, the part of our conclusion. Give me a new relation in between the structure of the component of the physical system, and provided we can provide it, this evaluated by the measure, the statistical complexity. Okay, this is some example with some different distributions. We can see that, okay, this is very ordered in this region, very disordered using different canoids that are localized in this region. But some chaotic system that we will see now are localized in the plane near to the maximum complexity. Well, we can see. But we can apply now, or we can explain how we apply the probability distribution. The problem is, given your system or time series, how we can define the probability distribution associated to this? Well, there's many different recipes, some like this. In particular, well, we can do it, we can consider the case of logistic map, And we can associate it, we can see what happened with the probability distribution. That is to say, okay, I don't remember that Christina showed, you can decide, okay, if I make some, in terms of the amplitude, we have this behavior is something that almost flat and almost in terms of the probability for white noise, we can say the probability distribution is an histogram. In the term of histogram is in the amplitude, all the amplitude appear almost with the same frequency. We evaluate with the statistical complexity. We see that in the case of logistic map, we see with this probability distribution, that is in this case, it will be H equal 1. The difference in term, this is in terms of the Euclidean distance. If you use Euclidean distance or whatever, or independent, we have again we have discussed a little bit more. But in the case of the probability by histogram, we see immediately this is 1, 0, and 0. The Fisher also is the opposite of behavior opposite to the Shannon or the entropy. In the case, we have for this uniform distribution, in the case of histogram, we have again 1, 0, 0 for complexity and Fisher 0. But this is something wrong, because chaotic dynamics is not a stochastic dynamic, and here we're using the probability distribution, we have exactly the same behavior, or the same as it. I take it two behavior, for one side, the logistic map, and a white noise, or random noise. I would take the same. Where is the error? Not in our form. The problem is that for a correct definition of the probability distribution, we must to take into account the time causality in the distribution, in the definition of the probability distribution. If we are not doing that, we obtain the wrong result. Okay. This is what we say. We must to include the time causality in the probability distribution. At least are two different ways to define a probability distribution associated with a time series, in which the time causality are taken into account for this definition. The first is the time probability distribution using the methodology of Bandt and Pompe, that we are explained. The second is using horizontal visibility graph or visibility graph directly. This is just two methods that are very, very easy to implement. In relation with the exercise, I I included the corresponding equation, the result for the code, or the code limited, for the different number of that you can consider. and between 3 and 6, or if you want to, I can include the program, but it's in Fortran. That's okay. Okay, then we can see. We can only analyze the case of Bandt and Pompe. This is more easy, and also was mentioned by Christina and something more. Okay. The problem is, given the system, how we can define the probability distribution associated to time series. Well, I mentioned something, some method, like frequency counted. Suppose you count how many words are in some book, how many these are classification in this book, and this kind of define a probability distribution. In the lexical store, we can define some probability distribution. The second will be making histogram of amplitude, or we can define a binary distribution. I mean, if there are some limit in your function or your data have separated a value, I say, okay, we assign 1, and if not, we assign 0, and then we have a binary string of some length, and you can use this for define our probability distribution for our problems. We can also make a Fourier representation. That means we can take the data, make a power spectrum, and associate to each frequency the amplitude in this power spectrum, and then we can define in terms of the power spectrum. You can also, but of course, in the Fourier are not including the information about the time that the frequencies appear, but okay, we can use wavelet. We can, it's a representation, and we can do it. Also, of course, ordinal patterns. With ordinal pattern, we make the basic. We can graphic our series and see the order, the sequence of parameters appears, and we define the different parameters. We want to discuss this later. And of course, the visibility graph. The visibility graph is you make a graphic representation and say you put in some point and see what is the following, if you can see the following point or not. If not, is borrowed by some intermediate point. It's quite easy. The last two, ordinal patterns and visibility graph, they are included the time causality, and by this you use this probability distribution, and this you say that this is the causality entropy complexity plane, and then we will say also the Shannon-Fisher causality plane. It depends if you are included or not the time causality. Okay. We can see a little bit more in the case of logistic map. This is the logistic map, okay? The diagram. We can see per R equal 4. It's chaos, totally developed chaos. Here, the different functions in terms of the range of the parameter. This is with Euclidean, in red. You can see red is the case of Euclidean distance for the disequilibrium. And this we can see. And here is the binary, in the case of binary, how we can change the probability resolution. This is the case of when we have a range and just that. And in definitive, we can see if we graphic in the logistic map, yeah, we see this is the case of the Lyapunov exponent, and we see that the graphic, if we use the Euclidean distance, all the values are near the curve of the minimum complexity, but this means that this part is for Lyapunov's negative Lyapunov exponent is great, more complex than the case of, in the case of chaotic, that this is not happen with the case of Jensen-Shannon. Yeah, you can see, you can repeat this in the practice, but this is why we need to use the causality in the probability distribution. I think, well, here is more graphics you can see. Okay, and we stop it here because we need to go to lunch, and tomorrow we start with the application. I explain a little bit more about Bandt and Pompe approximation and how we can see about the entropy complexity plane, and we call complexity plane Shannon-Fisher entropy plane, causality plane, yeah, and some application.
Any question?
Yeah.
Yes, okay, then we continue tomorrow. Thank you very much,
Okay.
Osvaldo.